So we move to the flash talks, and the first one is from Sarah Keep from the Pirbright Institute.
I'll jump straight in. So I work on infectious bronchitis virus, or otherwise known as IBV. The focus of my work has been using reverse genetics to rationally attenuate the IBV genome. The reason we do this is we're trying to make the next generation of live attenuated vaccines. Current vaccines are made by taking a virulent field isolate and passaging it 80 to 100 times in embryonated hens' eggs. Molecular mechanism of attenuation is unknown. There's a balance to be had between attenuation and retention of immunogenicity, and there's a real risk of reversion because these viruses still have a virulent population at the subconsensus level. So a virus I made quite early on in my career is a virus called M41R. It's a recombinant IBV based on the M41 genome, which is virulent. Now, M41R contains 4 single point mutations, one in NSP10, one in NSP14, one in NSP15 and 16. And M41R is attenuated in vivo, and it has a temperature-sensitive replication phenotype. And what we discovered early on is that those 2 phenotypes are associated with the mutations in NSP10 and 14. And when you use M41R as a vaccine, a single dose will elicit 100% protection from challenge. And IBV, whether an IBV vaccine works is done on tracheal ciliary activity. This is post-challenge data, and you can see that the activity is the same as the mock vaccinated mock challenge group, which is lovely. So when we look at the mutations, there's NSP10 and 14 that do most of the work, and the residue in NSP10, so that's at number 85, and the residue in 14, which is 393, is conserved, not only amongst the many strains of IBV, but also in the wider coronavirus family. So before getting too excited, what we wanted to check was that these mutations would work in another strain of IBV. So we picked a strain called D388. It's highly pathogenic, it's systemic, and it's a different genotype and serotype than 41. So this is some of the data on the poster, and what we saw was partial attenuation. But these birds got a whopper of a dose, so it is quite positive. And then what we're doing now is looking at whether we actually need the other mutations in 15 and 16 for full attenuation, and we're really looking at reversion potential. So when we first did this work, we passaged at permissive temperatures and we didn't see any reversion. But now we are looking at non-permissive temperatures and intermediate permissive temperatures. And my placement student, Amber, has done a brilliant job. And she's identified some changes in NSP14 that may be associated with reversion, but this was not easy to do. It took several attempts. We're also looking at how the mutations are working. So the mutation in NSP14 is in the capping domain, and we've been working with Trevor Sweeney's group at Pirbright to set up a capping assay for IBV. So we've been expressing wild type and mutant versions of NSP14 and 10, and then doing this in vitro capping assay. And Amber has managed to get this assay working, and it looks quite positive. So any questions, come and see the poster. It does have a lot of data on, and this is like 20 years worth of work. So a lot of people have helped, and I know some of them are in the room. So thank you.